You're standing on the sidewalk in a heavy thunderstorm. The rain hits the asphalt, rushes toward the curb, drops through an iron grate, and disappears. For most of us, the problem is solved. The street stays clear, and modern life continues. That iron grate is the intake valve for an aggressive, entirely invisible machine operating right beneath your shoes. Look at this 3D layout of a city block. Modern urban centers are built on absolute impermeability. Concrete, asphalt, glass, and steel roofs prevent the earth from acting like a natural sponge. When rain falls here, 0% of it is absorbed. Every single drop becomes immediate surface runoff. To see the impact of that design, consider the math. When exactly 1 inch of rain falls on a single square mile of this dense grid, it generates over 17 million gallons of water in a matter of hours. With nowhere to sink into the earth, water seeks the lowest point. Without engineered intervention, it flows directly into subway tunnels, basements, and skyscraper foundations. The entire metropolis becomes a bathtub. To survive this reality, civil engineers had to build a secondary landscape underground, designed exclusively to swallow the flood. The front door to this subterranean system is the catch basin. Beneath the iron grate sits a precisely engineered mechanical trap. When rainwater rushes off the slope of a street, it carries a heavy payload of physical debris. Gravel, leaves, plastic bags, and street trash are swept up in the current. If that material flowed directly into the main tunnels, the city's underground arteries would clog and back up within minutes. This diagram shows a cross-section of a catch basin to explain how it prevents those blockages. Notice the exit pipe that carries water away to the sewer system. It is positioned halfway up the interior concrete wall, leaving a deep pocket below. When the flood pours in, the heavy gravel and trash sink to the deep bottom of the vault, the sump. The lighter, clean water rapidly fills the vault, rises up, and spills over into the exit pipe. It is an entirely passive sorting mechanism. To keep these traps from filling up, fleets of city maintenance trucks equipped with industrial vacuums routinely deploy long hoses to suck the accumulated debris out of the sumps. Once the clean water clears that exit pipe, it officially enters the hidden system. It flows into lateral pipes, connecting to massive trunk mains buried deep beneath the avenue. Here, the entire network runs on a single, perfectly calibrated engine: gravity. This animation illustrates a calculation known as self-cleansing velocity. Every single pipe is laid at a specific downward angle. If the pipe is laid too flat, the water moves slowly and sediment hardens, blocking the flow. If the pipe is pitched too steeply, billions of gallons of rushing water would achieve a velocity that acts like a sandblaster, destroying the concrete walls. Engineers calculate the exact slope to move water fast enough to scour the pipe clean, but slow enough to leave the infrastructure intact. This delicate balance solves micro-level blockages, but it routes the massive accumulated volume of thousands of streets toward a single city-wide crisis point. As the trunk mains gather water from thousands of individual streets, they merge into interceptor sewers. The flow transforms from a corner trickle into roaring, pressurized subterranean rivers, rushing through concrete and brick tubes large enough to drive a semi-truck through. This intersection introduces a major operational vulnerability built into older major cities during the early 20th century. This flowchart highlights the design of a combined sewer system. Under this design, the rainwater collected from street grates flows into the same underground pipes as the raw sewage coming from the toilets and drains of the buildings above. On a dry day, this combined flow moves to a wastewater treatment plant. But during a heavy thunderstorm, the math breaks down. Billions of gallons of sudden rainwater flood the system, pushing the volume past a critical danger threshold. Without an escape route, the pressurized water would destroy the treatment plant, or force geysers of raw sewage up into residential basements. To stop the pipes from bursting, these systems feature an emergency release valve known as a combined sewer overflow. When the water hits that limit, it breaches a concrete weir. The massive tidal wave of rainwater mixed with raw sewage completely bypasses the treatment plant and is dumped directly into the city's rivers, lakes, or oceans. The release valve keeps the physical city from drowning, but it trades an infrastructure failure for a massive environmental disaster. Solving that pollution problem has required a multi-billion-dollar brute force engineering response. Because engineers cannot easily dig up every street to separate the pipes, they descended far beneath the subway lines and skyscraper foundations to build the ultimate solution: deep tunnel and reservoir systems. To create these networks, colossal automated tunnel boring machines, some over 50 feet in diameter, have carved out concrete-lined caverns directly into the bedrock. During a megastorm, when the standard gravity pipes hit their breaking point, automated steel gates slide open. The roaring floodwaters are diverted, dropping violently down vertical shafts into pitch-black holding tanks. These holding zones have an immense scale. Some are large enough to fit entire cathedrals inside them, engineered to hold tens of billions of gallons of pressurized water until the storm passes. A moment of wonder. Up on the surface, people walk with umbrellas and traffic flows. The city remains stable, entirely disconnected from the violently churning subterranean ocean, trapped hundreds of feet beneath their shoes. Once the storm ends, the system faces a final operational hurdle. Because these deep rock tunnels are carved hundreds of feet beneath the natural waterline, gravity can no longer move the water. The holding tanks must be emptied before the next storm arrives. This requires the staggering industrial force of massive turbine pumping stations. Often hidden inside windowless brick buildings or buried beneath public parks, these house-sized pumps roar to life, lifting millions of gallons of heavy water hundreds of vertical feet back to the surface treatment plants. The modern paved city fundamentally defies nature. We have sealed ourselves inside a concrete landscape that should, by all laws of physics, drown the moment the weather turns. But the next time you watch rain hit the curb, remember, you are standing on top of a perfectly controlled subterranean river, constantly working to keep the metropolis alive.